Hello, welcome to this session where we shall be looking at the proposed memorandum for the Johannesburg West November examination. Okay, so for those learners or districts that have not written, we can probably use this as our revision guide and preparation. Okay, so the paper is 3 hours out of 150 marks. Okay, and then it is a PLC paper. Instructions, we have 10 questions that we need to really answer. And yeah, okay, question number 1. Which of the following is a non-contact force? Okay, non-contact, it's basically the gravitational force. So C is the correct option there. And then the frictional force that is acting on a sliding object is dependent on the apparent area of contact. Nope. Is proportional to the normal force. This one is okay because we know that frictional force is mu multiplied by the normal force, so it's proportional. So dependent on the velocity, nope. Independent of the type, no. So B is the best answer in that case. And then 1.3, a constant force Fa acts on an object causing it to move at a constant speed of a rough horizontal surface as shown in the diagram. So how does the force of friction compare to Fa? Okay, what do you see? F friction is the same as that. That is a no. FF is greater, frictional force is greater? No. The fact that the object is moving at a constant speed, then definitely this applied force needs to be greater than the frictional force. F friction is less than that? Yes. F friction is 0? No. The surface is rough, so frictional force cannot be 0. So C is the most accurate answer for 1.3. And then 1.4, two isolated bodies A and B that are having masses m and 2m respectively are placed a distance r apart. Consider the following statements regarding the gravitational force that will be exerted. So the force exerted by B on A is half. Nope. Remember, the force that is exerted between the two needs to be, is it the same? Let's see, I don't know. 2, the force exerted. Okay. The force exerted is independent on the masses. No, the force must be dependent on the masses. The force exerted by body A, B is equal and opposite. Yes, so the force is the same regardless of the masses and what the direction is going to be opposite. Then the forces will always be attractive, which is true. So 3 and 4, which is option C. Okay, and then 1.5. Two objects M1 and M2 at distance r apart experience a gravitational force F. Then the mass of one body is now halved. So you're going to have half of a mass. And then the diameter is doubled. Okay, so if you double the diameter, you're going to have something like that. So initially, G is going to be, F is going to be G M1 M2 over R squared. So here we're going to have a G, a half M, and then that. So you're going to have a half G M1 M2 divided by 4R squared. So if we have a half, okay, and then multiplied by 1 over 4 or divided by 4, which is the same as multiplied by 1 over 4, which means we're going to get 1/8 of F. Okay, so for 1.5, the correct option that I'm seeing is A. And then 1.6, the electric field pattern between two charged spheres A and B are shown below. Which one of the following statements is correct with regards to the spheres? So A and B are both positively charged. This makes sense, but no, it's not. It doesn't make sense because if they were both positively charged, then we would have just a region of space where there is no field lines moving. So when I look at the field lines, B should be a positive and then A should be a negative since the field lines are entering. Sphere A and B are both negatively charged. Nope. Then A is positively charged. B is no. So A is negatively charged and B is positively charged. So D makes more sense for 1.6. And then we know that an electric field is a region in which a charged particle experiences an electric force. Okay, there is some bit of truth in that. Is the energy per unit charge experience? No, it's the force. Okay, and it's directly proportional to the product of current and resistance. No, that is charge. Is the rate of work done by that is power. So let's go with option A as the best. 1.8. Which one of the following can be used to measure the current in the conductor X and the potential difference across its ends? Which one of the circuits below can be used to measure the current in X and then that? Okay, so looking at this, we need to see how is the voltmeter connected across the X conductor. Okay, so if this is X, the voltmeter is connected across the terminals, which is fine. When you look at this, it's like the voltmeter and the X are connected in series, which is wrong because it has to be connected in parallel. Then when you look at this, the way X is connected, there's some bit of sense in it, but the question wants us to measure the current and the voltage. So the ammeter must be connected in series, which is fine. And then the voltmeter, so this voltmeter is connected in, it's going to be in series with the ammeter, which doesn't make sense. And then these ones, they're all connected in parallel, which is wrong. So the options I'm seeing, there is some bit of truth in D, and there's some bit of truth within option A. Okay, but since I know that X and the voltmeter must be parallel, so I'm going with A as the most suitable answer there. Okay, because voltmeter, ammeter in series, no. Then 1.9, which one of the following graphs best represents the relationship between electrical power and the current? So we know that power can be given as IV, the product of current and the voltage. So which option can best describe this? So what we have, this is power, this is current. It's constant, no. Inversely proportional, no. But, okay, we have this, but then we also have I squared R. Okay, that's also one other representation of power and current. Okay, so options C and D make some bit of sense. But now the fact that we have this I squared, and if we say that R, but we never said R, option C or option D, power is directly proportional to the current. So let me take option C for this case, if I'm focusing on this, meaning that the gradient is just going to be the voltage. Okay. All right. In a given ohmic conductor. Yeah, I think C makes more sense. But between C and D. Okay, 1.10, in the diagram below, the north pole of a magnet approaches end A of the solenoid. Okay, which one of the following statements about the polarity in the direction will be based? So if this is the north, okay, what is our A gonna be like? So there's a north pole that will be induced there. Okay, and then if we're focusing on the north, which means we're looking at B and C, then what will be the direction of the field? Okay, the direction of the field is going to be B to A. Okay, it's going to be B to A, which is option B. Okay, so that is the MCQ. Question number 2, 2 light ropes are strung between two vertical struts. A mass of M of weight W hangs from the ropes, and they're attached to a ring at point Y. Okay. Then they want us to define what resultant vector is. So we know that resultant vector is more like the sum of two or more vectors. You can say that sum of two or more vectors. Okay, someone can also say that it is a single vector, okay, that has the same effect as two or more vectors together. Okay, single vector with the same effect as two or more vectors. Then 2.2, are the forces acting on Y in equilibrium? Okay, yes or no? Two ropes are strung, a mass of weight hangs. Okay, the question is, it hangs, it's not moving away, so meaning that it is in equilibrium. The answer is a yes. Okay, and then we're going to say that the mass remains at rest. Okay, it remains at rest. And if it's remaining at rest, it simply means that the net force is 0. Then 2.3, the tension that is acting on the rope P is 600 newtons. Can we calculate the tension that is in Q? So there are two ways to do this, okay, or even three ways. Number one, we can start by trying to resolve these forces, okay? When you look at this object Y, we know that the weight is going to be downwards. If I resolve this, meaning that I'll have a component, okay, if this is a 30, this is going to be a 60. And then if this is a 60, then this is going to be a 30. So meaning that my tension up is going to be Q, the sine of 30, or Q, the cos of 60. Okay, and then this side, I'm going to have P, the sine of 60, or P, the cos of 30. That will be acting upwards. And then besides that, is there any other force of interest that we can get? Not really. There is no other force. So meaning that if we are to look at the P, okay, let me just look at the horizontal. It's going to be P. Why don't I just resolve this thing that side and say that one, I have my weight, and then this is our Q. This is the horizontal, and I'm gonna have this as our P. Okay, so resolving this, we say this angle is going to be a 30 because that was a 60. And then this angle here is going to be a 60. Okay. And then we're also going to have that. Okay. So what we are saying is that we have the PX, since it's in equilibrium. PX is also going to be the same as the QX, the horizontal components. So this is going to be P cos of 60. This is going to be Q cos of 30. Okay, just equate the two. We know that's going to be a 600. Cos of 60 should be equivalent to Q cos of 30. So we know that the cos of 60 is a half. So half of 600, that's going to be 300 divided by the cos of 30. And that should give us our Q. So the answer I'm getting is a 346.41 newtons. All right, so the tension, we have the Q, 346.41. And then they want us to get the mass that is hanging, the mass M hanging from the two ropes. So then we can do the vertical forces and see what's going to happen. So if I'm to focus on the vertical forces, number one, I need to start by getting the weight. But this weight is going to be equivalent to the P Okay, this upward one. It's going to be a P sine of 60. It's going to be a Q sine of 30, which we already know. And then I'll equate it to the weight that is acting downwards. So we are saying that P sine of 60 plus a Q sine of 30 is equal to the weight. Okay, the P is a 600 sine of 60, 346,41 sine of 30 is equal to the weight, which is, we can say mg, okay, whereby the g is the 9,8. Now we shall replace that. So this first part gives me a 519,62 plus 173,21 is equal to 9,8 m. When you plus that together, we get a 692,83. I'm dividing it by 9,8, and then this gives me 70,70 kilograms. Okay. Then question number 3. Two blocks, A and B, resting on rough horizontal surface are connected by a light string. Okay. The blocks A and B have masses 16 and 24 respectively. There is a constant force of 120 that is acting at 64 degrees the horizontal. The two blocks accelerate to the right with this constant acceleration. Can we define the term kinetic friction force? So basically, we know that this is a force that opposes motion that is relative to the surface. So a force opposing the motion of a moving object, because the object has to be moving. Okay, moving object relative to the surface. Okay, and then 3.1.2 draw a free label diagram for the 24 kg. So if I look at the 24 kg, okay, we're going to have the force applied. We're going to have the weight. And then we're also going to have the tension. We're also going to have the frictional force. So the Fk. And then we're also going to have the Fn, which is the normal force. So that should give us 5 marks, okay? Frictional force, tension, weight, and all of that. So that is everything that we're going to have there. And then the weight, okay. So those are the 5 marks. And then 3.1.3, they want us to calculate the normal force on B. Now, when you look at the normal force on B, remember there is a component of the force applied. Okay, meaning that if we get the normal force plus the Fa of y, this should give us the weight downwards. Okay, so if we are to resolve this up, so this is Fay acting upwards, Fn is upwards, it should be equivalent to the weight. Meaning that our normal force should be the weight, W, minus the Fay. Okay, let's do the substitution. So what is the weight? So it's going to be the 24 multiplied by 9,8 minus the applied force is 120. So that's going to be 120 the sine of 64. Okay, so when you punch this in the calculator, we're getting 124,80 newtons. All right, then 3.1.4. 3.1.4. They're asking us for the coefficient of kinetic friction on B. Coefficient of kinetic friction on B. Okay, so before we get the kinetic friction on B, we can use the F net and get the frictional force, first of all. But we also need the tension. That's also another thing. Unless if we're going to combine the entire system and ignore the tension, so that we end up with just, but either way, we have to solve these things simultaneously. Okay, so when I look at A, we're going to have tension, frictional force, we're going to have the weight, and then all of that. Is this going to help us? But as long as we don't have the coefficient of kinetic friction, it's going to be hard to get the tension. But that can be worked out. Not so. Let's give it a try and see how we're going to work this out. So let's start with A. Let's start with A. So we're saying that from block A, you know that F net is equal to MA. Forces acting there is just the tension minus the Fk should give us the mass, which is like MA. Tension, we don't know. Okay. Minus, what do we know about block A? Are telling us that the 16 kg experiences a frictional force. So we have the frictional force of A, which is 3,5. Okay, is equivalent to 16 multiplied by the acceleration, which is 0,988. Okay, then for me to get my tension, it's going to be the 16 times 0,988 plus the 3,5. This becomes 19,308 newtons. So that is our tension. Okay, then we go to block B. When you look at block B is being affected by just the horizontal component, which is going to be 120 cos of 64. So let's apply the same thing, that F net is equal to MA, meaning that the 120 cos of 64 minus the tension that we got. Oops, let me just write it out before I do the substitution. So the FAX minus the tension minus the frictional force should give us the MA. So we said 120 cos of 64. We are subtracting the 19,308. We are subtracting the Fk should give us the 24 times the 0,988. Okay, so when I do my magic, I have to move this one that side, move this one this side. Okay, and what is that going to give us? I'm finding my Fk to be the 120 cos 64 minus 19,308 minus 24 multiplied by 0,988. So this gives me just a 4 newtons if I round it off. Now, we know that the frictional force is given as mu multiplied by the normal force. Okay, say mu k. So 4 is equivalent to mu k multiplied by the normal force that we calculated. Okay, did we? Yes, calculated it to be 124,8. Okay, then let's divide both sides. So it's 4 divided by 124,80, and this gives us a 0,03. Remember, we shouldn't have a unit for this mu, and our answer should never be greater than 1. Okay, so that is question 3. Question 4, 2 blocks of different masses are attached to each other by light string T2, which is placed over a frictionless pulley. Block A with mass 2 kg is placed on the rough surface and then attached to the wall by a second string, which makes 70 degrees as shown. The entire system is in equilibrium. State Newton's law of motion, Newton's second law of motion. So one thing we know about this law is that when a net force, okay, when a net force acts on an object, what happens? The object will accelerate. Okay, object accelerates in the direction, okay, in the direction of the net force, in the direction of the net force. Then the acceleration, or with an acceleration that is directly proportional. Okay, directly proportional to the net force. Directly proportional to the net force and inversely proportional to the mass. inversely proportional to the mass of the object. And they want a free body diagram for the 2 kg. Okay, so the free body diagram, how many marks is it? Is 5 marks. So which means you need 5 forces. So T2 here, we have T1. There is weight. There is normal force. There has to be friction, because it's just placed on a rough. So frictional force, Fk. So translating this into the forces, we have the weight, we have the T2, we have the Fk, we have the T1, and then we have the normal force, Fn. Okay, so those are the 5 forces for the 5 marks. And then determine the magnitude of T2. So we know that this T2 is the same as the T2 that is acting here. So when you look at the 5 kg body, it's just T2 and then the weight that is acting downwards. So T2 is just going to be 5 multiplied by 9,8. Okay, 5 multiplied by 9,8, which becomes 49. Okay, and then they're telling us that the static frictional force on the 2 kg is 10,47. Can we show that the magnitude of the normal force is 5,58? So still, even with this question, since we have a force at an angle, meaning that if we resolve this into a 30, we're going to have a T sine 30 moving upwards, meaning that our force normal plus the T sine of 30 must give us the weight. What does the question want? Show that the normal force. So we're looking for this. So our normal force is going to be the weight minus the T1 sine of 30. And what is the size of T1? Do we know the, okay, we can start by finding that T1 using the horizontal components, since we have the frictional force here. Is that true? Yes, we can do that. We can do that. Okay, so we said start by looking for the T1 before we can do the substitution into this. Okay, so T1 horizontally, we're going to have a T1 cos of 30 plus the frictional force should be equivalent to T2, because we already have what T2 is, meaning that T1 cos of 30 is equivalent to the T2, which is a 49, minus kinetic friction, not static friction, which is a 10,47. Then I'll divide this by the cos of 30 so that I get what T1 is. So 49 minus that, we get a 38, something. Okay, when I divide by the cos of 30, I end up with just 41 newtons. Then, remember what we say, that our Fn, okay, Fn is going to be the W, okay, which is the weight, which is 2 times 9,8. Does that make sense? It's the other way around. It is the other way around. So if this is moving this side, this must move upwards. Okay, so what is 41? We subtract 2 times 9,8. Okay, so 41 minus, no, something is off here. Something seems to be off here. Let me just punch this into my calculator again. Okay, punching this in the calculator. We're saying 49 minus 10.47 divided by the cos of 30. Is it a 30? No, it's not a 30. It's a 20, because 20 and 70 is a 90. Meaning that even this is wrong, because it's going to be a 20. Okay. Okay, so this is a 20 as well. Okay, so cos of 20, I get 41. Okay. Now, if the T1 is that, we're saying the weight. Okay. The weight, I'm just substituting that. Okay. It's going to be the weight, which is 2 multiplied by 9,8 multiply minus 41 sine of 20. Okay. So 2 times 9,8. We are subtracting 41 sine of 20. I'm getting 5,577, which is 58 newtons. Okay, which is fine. Okay. And they want us to determine the coefficient of the static friction between the 2 kg and the rough surface. So we need to get the frictional force. Okay. And we know that F net is equal to 0 since the system is not moving. So if we have our T2 minus, we're saying the T1 cos of 20 minus the Fk should give us a 0. It's supposed to be Fs for static friction. Okay, so we have what T2 is, we have what Q, so meaning that we need Fs. That's going to be T2, which we got as 49 minus 41 cos of 20. Okay, so 49 minus 41 cos of 20 gives me 10,47, but it's just the same surface, ne? So I don't know why I'm going back there. Okay, so let's get the, so Fs is mu multiplied by normal force. So it's going to be the 10,47 divided by the normal force. So by the 2 kg, we've calculated our normal force to be. Is a part where we calculated the normal force that it's here actually. It's 5,58. So divided by 5,58. Does that make sense? It should make sense. So 10.47 with the calculator divided by 5,58. I end up with 1,876, which is 1,88. Okay, so since it is static friction, yet it's allowed for the value to be greater than 1. All right, question 5. The acceleration due to gravity of a planet is this. The radius of the planet is 1/3. Okay, of the radius of the Earth. Explain the difference between mass and weight. Okay, so one thing we know is that mass is the amount of content or amount of body. No, it's the amount of content in a body or the amount of matter or substance in a body. 2, this mass is a scalar quantity. Okay, scalar quantity that is measured in kilograms. Okay, and then weight, on the other hand, is a gravitational force that is exerted on the object. Is the gravitational force on an object by the Earth. Okay, it's measured in what we call the newtons, and it's a vector quantity. All right, then 5.2, they want us to calculate the mass of planet X. So what we're going to do, since we have the gravitational force, we're going to say G is equal to G m over r squared. We are interested in the mass. So meaning that the mass is going to be gr squared divided by the capital G. So we substitute that. So what is our G? And we know that our G is going to be a 2,7. And then the radius, they told that it's a third, the radius of the Earth, which means it's 1/3 multiplied by 6,38 multiplied by 10 to the exponent of 6, but this must be squared. And then we are dividing it by the constant 6,67 times 10 to the negative 11. So punching this into the calculator, the mass that I'm getting is 2,7 times that squared, 1,83 times 10 to the 23 kilograms. Okay, then 5.3, determine the factor by which the weight of an object on planet X will differ from the weight of the same object on this. So the factor should be by the gravity. Okay, so on Earth it's going to be a 9,8. On that planet it's going to be a 2,7. Simplify this, you get a 3,63 times. Okay, whether smaller or bigger, that is what happens then. Okay, and then we can say smaller since they say the radius is smaller. Okay, question number 6. The diagram below shows the two spheres that are identical, R and S, placed on distance. They carry 11 and negative that. And then the spheres are brought into contact for a while and then they are separated. One reason why the spheres will be placed on insulated stands, number one, to avoid leakage of charge. Okay, to avoid leakage of charge so that the spheres do not lose any charge. Okay, so then 6.2, calculate the charge on each immediately after the separation. So we're going to get the charge on R plus the charge on S divided by 2. So 11 plus a negative 7 divided by 2. That gives us a 6 divided by 2, which is a 3. Ne? Am I on the same page? No, it's a 4 actually, because 11 minus 7 is a 4, which is a 2, but microcoulombs. All right, then 6.3, they want us to draw the resultant electric field pattern after the separation. So both of them are going to be positive, okay? And if both spheres are positive, it simply means that there's going to be some bit of repulsion that is taking place. So what we are interested in is basically the direction of the field lines and then the space that will be created. So field lines must be seen to be moving out of the spheres. Okay. So something like that would guarantee us those 3 marks. Okay. Then 6.4, can we show the number of electrons transferred from S to R during the contact is this much? So let's use sphere R. Okay. Originally it was 11. And then finally we have a 2. So how many electrons were transferred, or how much charge was transferred? So change in charge, we're going to get 11 minus 2, which gives us 9 microcoulombs. Okay, can be positive or negative. Then for us to get the number of electrons, we're going to get Q over E, which is 9 times 10 to the negative 6 divided by the electron charge, 1,6 times 10 to the negative 19. Okay, quantization of charge. So this gives us the 5,63 times 10 to the 13. Alternatively, you can use S, whereby you get the final minus the initial, and then you end up with a 9 microcoulombs. Okay, that is question 6. Question 7, two identical negatively charged spheres, X and Y, having charges of the same magnitude, okay, are placed 500 millimeters. Now they are saying millimeters here, they are writing meters. Okay, so the magnitude of the electrostatic force on the spheres is this much. Okay, can we state Coulomb's law in words? And so Coulomb's law simply tells us that the magnitude, okay, of the electrostatic force that is exerted between 2-point charges exerted between 2-point charges or between one charge onto another, okay, is directly proportional to the product, okay, of the magnitude of the charges, and inversely proportional, okay, inversely proportional to the square of the distance between them. All right. And 7.2, they want us to calculate the magnitude of the charge on each of the spheres. Now, one thing we know is that the charges have the same magnitudes. No? So we know that F should be K, Q1, Q2 over R squared. So the force they gave us was 0.288. The K is a 9 times 10 to the 9. Then I'm going to say that is Q squared. The distance between them, they told us 500 millimeters. Okay, change this to meters, which will be 0.5, but squared. Okay, meaning that my Q is going to be the square root, get the 0.288 multiplied by the 0.5 squared over the 9 times 10 to the exponent of 9. What does the question want? Calculate the magnitude of charge on each sphere. Okay, so what I'm getting, if I punch this into my calculator, saying square root 88 times 0.5 squared over 9 times 10 to the 9. Oops, so 3, 6. So I'm getting 2.828 times 10 to the negative 6 coulombs, okay? Now the sign after the separation, no, 2 negatively charged, so which means the charge is going to be negative. Okay, so that is what I get for that particular question. And then P is a point that is 800 millimeters away from sphere Y. Okay, so we got the charge for each one of those and then define what electric field at a point means. Okay, so we know that electric field is basically the electrostatic force. Okay, electrostatic force experienced per unit positive charge. Per unit positive charge that is placed at that point. Okay, then what is the direction of the net electric field at P? We choose left or right. So if this is a positive, this is a negative, that's a negative. When you look at Y and P, P is going to experience some sort of attraction because the signs are opposite, so it's going to be in that direction. Okay, when you look at X and P, there's still attraction. It's going to be pulled that side, meaning that the net should be operating in the same direction, so which is going to be left. And then 7.5, the number of electrons that must be removed from sphere Y so that the net electric field is this 7. Okay, so we're going to start by looking for the net. Okay, before we look at sphere Y. So what we're going to do, we have the net electric field, meaning that the EK of X plus the EK of Y should give us 4 times 10 to the 4, but this is now to the right. Okay, there's no problem. There is no problem, but then if that is the case, then it simply means that we're looking for the charge on Y. Okay, does that mean we are playing ignorant? Okay, let's play ignorant and say we don't know the charge here. And we do the subtraction, because if now we are getting a different result, and which means there's something else on Y. Okay, so we're going to say that KQ over R squared, KQ over R squared must give us the 4 times 10 to the 4. Okay, 9 times 10 to the 9. The charge on X we found it to be 2 comma, we said 8 what? Where did we write it? It was this side. So it was 2,82 times 10 to the negative 6. The distance for x, when we look at the x, it's going to be the 800 and the 500, which is 1.3. Divided by 1,000, which gives us 1,3. So over 1,3 squared minus 9 times 10 to the 9 multiplied by the q of y over, it's actually supposed to be the other way around. Supposed to be the other way around. And then the distance between y and is 0,8 squared. Should give us 4 times 10 to the 4. Okay, so this must be moved that side so that we have an addition and then multiplied by that. Okay, so if I do my simplification, okay, the simplification that I'm getting after everything, so q of y is a 3,92 times 10 to the negative 6. Okay, now we want to see the difference. Okay, the difference between the charges. So if this is what we have, and originally we had a 2,828, okay, if we do the subtraction here, so 3,92 times 10 to the negative 6 minus 2,828, this gives us a 6,74 times 10 to the negative 6. The question is asking us how many electrons must be transferred. So come this side and tell us that N should be Q over E. So 6,74 times 10 to the negative 6 over 1,6 times 10 to the negative 19. And this becomes 4,22 times 10 to the 13 electrons. Okay, so that is what was supposed to be done. Then question 8, in an experiment to verify the relationship between electrostatic force and the distance r between two identical positively charged spheres, the graph below was plotted. 8.1, what is the relationship, or what relationship between electrostatic force Fe and the square between the charged spheres can be deduced from the graph? So for as long as we have 1 over r squared, and then this is F, which means it is inversely proportional. So it's inversely proportional to the square of the distance. Okay. Then 8.2, write down the dependent. So the dependent is basically the force. The controlled in this case is going to be the magnitude of the charges. Okay, because we can control the charges to be fixed. And then lastly, use the information to calculate the charge on each sphere. So if we get the gradient, will it give us something reasonable? Okay, so we know that the spheres are identical and they are positively charged. Okay, meaning that the change in F over the change in the distance, which is 1 over r squared. We can look at which point. Any point of interest, 0,025. Can we use this? Or we can use this point here. I don't know the reading of it. But by the looks of it, it's 5, 1, 2, 3, 4, 5, 6. It's 5,6. And then this is going to be like a 0,27. Okay, so let's use that and say that we have a 0,027 minus 0 over 5,6 minus 0. This becomes a 4,82 multiplied by 10 to the negative 3. Okay, now one thing we know When you look at that Coulomb's formula, it's KQ Q over R squared. Okay. Now, when you multiply this, it's going to be R squared alone. You have to divide by the K and then find the square root. Okay. So what is it going to become? It's going to be 4,82 times 10 to the negative 3 is equivalent to 9 times 10 to the 9 with a Q squared. So divide by 9 times 10 to the 9. And then let's get the square root. So meaning that Q should be a 7,32 times 10 to the negative 7 coulombs. All right, then question number 9. Learners conduct an experiment. Okay, as we can see, and that's the graph. Use the graph to determine the EMF. So EMF is where the potential difference starts from. So it's basically 1,5 volts. And then they want us to get the internal resistance without. So internal resistance, we just need to calculate the gradient. Okay. So what's going to be the gradient? We're going to say that the change in I over the change in V. We know that V is equal to IR. So we're going to flip it afterwards. Okay, so change in I is going to be 1,8 over the 1,5. Or we can do it the other way around and say 1,8 minus 0 over 0 minus 1,5, something like that. So the answer we're getting is a negative 1,2. And then we know that this represents 1 over R, should be equivalent to the 1,2. Cross multiply, so R is going to be 1 over 1,2, which becomes a 0,83 ohms. Okay, so that is how we were supposed to get that. Then a battery with some unknown EMF and an internal resistance are connected, as we can see. They want us to state Ohm's law in words. So we know that Ohm's law tells us that the potential difference that is across a conductor, okay, is directly proportional. Is directly proportional to the current. Directly proportional to the current at a constant temperature. At a constant temperature. Then switch S1 and S2 are closed, as we can see. And then the reading A1 is 1,5 amps. Okay. Calculate the reading of the voltmeter. Okay, so we need this. Let's get the voltage across this 2 and that. So we know that the resistance is going to be 7. Okay, it's going to be 5 plus 2, which is 7 ohms. And then we know that V is going to be IR. So 1,5 multiplied by 7. Okay, 7 times 1,5 gives us 10,5. Question is asking for the voltmeter. Now we know that these two are in parallel with this, so the voltage needs to be the same. So that's how we get that, and then we get the 10,5 volts. Then 2, they want the reading of A2, which is the total current. Now, for us to get the total current, we know that, is that going to make sense? I believe it should. If we look at the total current, I. So if the voltage here is a 3, let's get the current there. Voltage is I multiplied by 3, but the voltage is a 10,5 divided by 3 should give us the I. So 10,5 divided by 3 gives us a 3,5. Meaning that our A2, which is the total current, is going to be 3,5 plus the 1,5, which gives us 5 amps. Okay, this is 5 amps. And then the power dissipated by the 3 ohm, so we know that the current through the 3 ohm is going to be a 3,5. We can use power is IV, or we can use I squared R. So if it's I squared, it's going to be 3,5 squared multiplied by the resistance, which is 3. Okay, 3,5 squared multiplied by 3, I'm getting a 36,75 watts. Okay, so that is what I'm getting there. And then S1 is now opened while S2 remains closed. The reading on the ammeter changes to this. Calculate the EMF of the battery. So we can use the EMF formula, okay? But they're telling us S1 is opened. So let's see here. Okay, so let's analyze the circuit and see. So if S1 is open, okay, it simply means that no current is gonna get to this part. It's only this that we shall have, okay? The reading on the ammeter A2 gets to this. So there's a drop of current, okay, from 5 amps to this much. Then they want us to get the EMF of the battery. So for us to get that, I think we should, I don't know, should we just consider the drop that we have? I'm trying to look at it that way so that we don't really waste a lot of time. Okay, because from the EMF formula, we're going to have current into R plus the internal resistance. But we know what the internal resistance is. They told us it is unknown. Okay, so if the internal resistance is unknown, how do we go about that? I'm thinking of using because it's not going to make sense unless if I have to apply the lost volts and things. Because if this is now the new current, okay, meaning that either we have to start by calculating the internal resistance, even if I'm focusing on just the top part alone. So for me to get the internal resistance, I have to look at the entire system. Okay, so it was a 7 and a 3 in parallel, okay? So effective resistance R is going to be the product over the sum. So it's 7 times 3 over 7 plus 3, which is a 21 over 10, becomes a 2,1. This is our R external. Okay. Then if that is true, we know that the EMF is going to be the current before everything got messed up into the 2,1 plus R. Okay, is that going to make sense? Yes. It's supposed to be something like that. Okay, so that's going to be a 10,5 plus 5R is equal to the EMF. Let's call this equation number 1. Okay, then equation number 2, still the same thing. If I look for the EMF, when the current now has been dropped to a 3,64. Okay, so 3,64 into the only resistor is a 3 plus the internal resistor. When I simplify that up, or rather I can call this equation 2 and equate both. So 10,5 plus 5R is equivalent to, what is 3 multiplied by 3,64? That becomes 10,92 plus the 3,64R. Let's collect the like terms. I'm going to move this on that side. I'll move this on that side. So 5 minus 3,64 gives me 1,36R. And then 10.92, subtract the 10.5, that's a 0,42, divide by 1,36, divide by 1,36. So what is our R? It becomes 0,31. Okay, so if I have 0,31 as my R, I can now just substitute this into this equation or into the first equation, and then I get my EMF. So the EMF is going to be the 10,5 plus 0,31 multiplied by 5. Okay. 10,5, that's a 12,05 volts. So that is how I would have obtained my EMF for the 5 marks. Then how does the voltmeter reading change if S2 is now opened while S1 is closed? Now, by you opening this and closing this, the total resistance is going to increase to 7. Remember, initially it was just a 3. Now it's going to increase to just a 7. So step number 1, we're going to say that the total, choose the voltmeter reading. Okay, so before I choose the voltmeter reading, let me state this. So total resistance increases. Okay, if the total resistance increases, means that the total current or the current in the circuit decreases, and the V internal, the voltage internal, will definitely decrease. Okay, so overall the verdict is the voltmeter is going to increase. Okay, because resistance is directly proportional to the voltmeter. Okay, then question number 10. Question number 10, which is the last one. They're telling us that a square coil with sides 0,2 meters and 100 tons is placed in a region with a uniform magnetic field directed perpendicular to the plane. The magnetic field is this Tesla to this in a period of 0,05 seconds. State Faraday's law of electromagnetic induction in words. So we are saying that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change of magnetic flux linkage with the conductor. Okay, so the magnitude of the induced EMF across a conductor is directly proportional to the rate of change of magnetic flux linkage within the conductor. Then 10.1.2, target the change. Okay, so the change in the flux is going to be B multiplied by the A cos of theta. And so B is basically the field or the change in the field. And then the A is the area. Since it's a square, we're just going to multiply 0,2 by 0,2. Okay, and then the cos, we're going to use 0. So this is going to be 0,2 minus 0,8 multiplied by the area 0,2 times 0,2, and then the cos of 0. So this gives me it's 0,024 Weber. And they want us to get the average induced EMF for the entire coil during this time. So just substitute into the formula. We know that EMF is N multiplied by the change in flux over the delta T. So that's going to be 100 multiplied by our answer, which is a negative 0,24, 0,024 over the time 0,05. This is going to give me a negative 48 volts, or just a positive 48 volts. Okay, and then state 2 ways in which the induced EMF can be increased. Number 1, you need to increase the number of turns of the coil. Okay, and then number 2, you need to use a stronger magnet. And then increasing the speed. I don't know. Yes, we can do that as well. Then 10.0.4, the coil is rotated so that the plane is no longer perpendicular. The magnet, or is no longer perpendicular to the magnetic field. What effect does this have to the induced EMF? Right? Only increase, decrease, and so on. So if it's no longer perpendicular, then definitely the induced EMF is going to decrease. And what will be the explanation? Okay, so it simply means that as the coil rotates, a component, okay, so as the coil rotates, a component of the magnetic field decreases. Okay, and then 10.2, show the direction of the magnetic field in this. So it's just going to be in this sort, okay? So that is all we have to do, just indicating that. All right, so guys, that brings us to the end of this paper. I wish you guys all the best in your preparation and as we prepare for paper 2. Let's stop there for now.